Hi, this is Schwartz from MasterMathMentor.com. This is video AB34. The topic is average value and the second fundamental theorem of calculus. It covers the AB manual, pages 199 through 200. We are given a graph of f of x in blue. The shaded area can be expressed as the integral from 0 to 2 of f of x dx. Question: is there a rectangle that has base 2 whose area is exactly equal to the value of this definite integral? It is clear that this rectangle with base 2 has an area that is less than the integral from 0 to 2 of f of x dx. And it is clear that this rectangle with base 2 has a rectangular area that is greater than the integral from 0 to 2 of f of x dx. So there must be some rectangle with base 2 whose height is somewhere between 1 and 5 that has the exact area as the integral from 0 to 2 of f of x dx. And here it is. The blue rectangle with base 2 has an area that is exactly equal to the integral from 0 to 2 of f of x dx. This occurs when x is equal to c. And if we look at the point c, f of c represents the average value of the function. We will define this in the next slide. In order for the area under the function f and the area of the rectangle to be the same, the two green areas, first between the average value of f, and the second between f and the average value of f, must be the same. So speaking in general, we have a continuous graph of f of x on the interval a to b. Consider the integral from a to b of f of x dx, which is the area under the curve. So we now introduce the mean value theorem for integrals, not to be confused with the mean value theorem that we learned in the differentiation section. If f is continuous on the interval a to b, then there exists some number c on that interval a to b, such that the integral from a to b of f of x dx is equal to f of c times the quantity b minus a. What this says is that the area under the curve f of x between x equals a and x is equal to b can be expressed as the area of a rectangle with base b minus a and height of the rectangle at some point c f of c. It is possible that there is more than one value of c, as we show in the graph here. In this case, there are two values of c, but the value of f of c is the same. So what is this value of f of c? By the mean value theorem of integrals, f of c equals the integral from a to b of f of x dx over b minus a. And we call that the average value of f on the interval a, b. In number 1, which is the same problem that we looked at when we started this video, f of x is equal to x squared plus 1 on the interval 0 to 2. And you are first asked to find the average value of the function on that interval. So the average value of f is equal to the integral from 0 to 2 of x squared plus 1 dx over 2 minus 0. And this gives x cubed over 3 plus x evaluated from 0 to 2 over 2, which is 8 thirds plus 2 over 2. and multiplying both top and bottom by 3 over 3, we get 8 plus 6 over 6, and that gives 7/3. So the average value of the function is 7/3. In 1b, you're asked to find the value of c guaranteed by the mean value theorem for integrals. What this means is this. We have found the average value to be 7/3, as we see on the graph. We are now interested in the value of c that gets us to 7/3. And to do that, we set f of c, which is c squared plus 1, equal to 7/3. And that gives c squared is equal to 4/3, and c is equal to 2 over the square root of 3. So we can see by the graph that when x is equal to 2 over the square root of 3, our height is 7/3. And the area under the curve, f of x, from 0 to 2, will equal the area of the rectangle with base 2 and height 7/3. That height 7/3 is the average value of f on 0, 2. Number 2 asks to find the average value of f of x equals sine of x on the interval 0 to pi. So the average value of f is equal to the integral from 0 to pi of sine x dx over pi minus 0, which is negative cosine x evaluated between 0 and pi, which is equal to negative cosine of pi minus negative cosine of 0, which is 1 plus 1 all over pi, or 2 over pi. The value of c guaranteed by the mean value theorem for integrals sets f of c, which is sine c, equal to 2 over pi, and c is equal to the inverse sine of 2 over pi, which is approximately equal to 0.690. We can see the results on the graph. Technically, there are two values of c that will give sine of c equals 2 over pi, but we want the one closest to the y-axis. That is what the calculator gives. In number 3, you're asked to find the average value of the velocity function, which is equal to natural log of t over t, in the interval 1 to e. Taking the average value of the velocity is no different than taking the average value of a function. So the average velocity will equal the integral from 1 to e of natural log of t over t dt over e minus 1. To do this, we'll do a little u substitution, where u is equal to natural log of t and du is equal to 1 over t dt, and we will change the limits. So when t is equal to 1, u is equal to 0, and when t is equal to e, u is equal to 1, and we get the integral from 0 to 1 of u du over e minus 1. That becomes u squared over 2, evaluated from 0 to 1 over e minus 1, or 1 over 2 quantity e minus 1. We see the value of 1 over 2 e minus 1 as a horizontal line just below 0.3. Do not expect that this will divide the shaded section in half. It does not. Remember that the average value represents the height of the rectangle, where the area of that rectangle with base 1 to e will have the same area as the area under the curve. We show that rectangle with the left and top border in red, and we can see that the area in white will probably equal the area in blue above the red line, telling me that the average value is correct. Number 4 reads, the number of people waiting in line to enter a Las Vegas buffet between 7 p.m. and 8 p.m. is shown in the table. What is the average length of the line as approximated by the trapezoidal rule? Working in terms of minutes, our average length of line is the integral from 0 to 60 of L of t dt over 60 minus 0. And that will be, by the trapezoidal rule, 1/60th times quantity, 5/2 times 20 plus 25 plus 10 over 2, 25 plus 40 plus 15 over 2, 40 plus 30 plus 10 over 2, 30 plus 30 plus 5 over 2, 30 plus 25 plus 10 over 2, 25 plus 20, and finally plus 5 over 2, 20 plus 5. That gives 28.125, and that will be measured in people minutes. We have looked at that concept before. However, we will then be dividing by minutes, so our answer is the average length of the line is 28.125 minutes when we look at this over from 7 o'clock to 8 o'clock. When we look at the graph of our points and also our average value, it is reasonable to believe that the area between the blue points and the red line above the red line is the same as that area below the red line. Realize also, though, that this is an approximation because we really do not know what's happening between 7 and 7:05, or between 7:05 and 7:15. We are assuming straight lines, but that does not have to be true. Students get confused when thinking about the difference between the average rate of change of a function f and the average value of a function between two values of x. Are they different? Yes, they are different. The average rate of change of f between x is equal to a and x is equal to b is the slope of the secant line, which is f of b minus f of a over b minus a. The average value of f between x is equal to a and x is equal to b is our area under the curve, the integral from a to b of f of x dx, divided by b minus a. However, the average rate of change of f between x is equal to a and x is equal to b is the same as the average value of the rate of change of f between x is equal to a and x is equal to b. We already stated that the average rate of change of f between x is equal to a and x is equal to b is f of b minus f of a over b minus a. The average value of the rate of change of f between x is equal to a and x is equal to b is, by our formula, 1 over b minus a times the integral from a to b of f prime of x dx. But we know that the integral of f prime of x is simply f of x, evaluated from a to b, over b minus a, which is f of b minus f of a over b minus a. So saying the average rate of change of f between x is equal to a and x is equal to b, and the average value of the rate of change of f between x is equal to a and x is equal to b is asking the same question. The same concept works with straight line motion. To find the average velocity of a particle traveling in a straight line between t1 and t2, the method is based upon what kind of information you are given. If you know the position function s of t, it's easy. The average velocity is s of t2 minus s of t1 over t2 minus t1. If you are given the velocity function, v of t, then we use our average value formula. The average velocity will equal 1 over t2 minus t1 times the integral from t1 to t2 of v of t dt, which is s of t evaluated from t1 to t2 over t2 minus t1, and we get our same answer, s of t2 minus s of t1 over t2 minus t1. If you know the acceleration function a of t and v of t1, we can use our integration formula, v of t equals the integral of a of t dt plus c, to find v of t. We will have to use v of t1 to actually find the value of c. And now we can use our average velocity formula again. In question 5a, suppose you were asked to take the integral from 1 to x of t squared minus 4t plus 1 dt. This presents no problem. We integrate the expression with respect to t and get t cubed over 3 minus 2t squared plus t evaluated from 1 to x. That gives us x cubed over 3 minus 2x squared plus x, minus the quantity 1/3 minus 2 plus 1, and that is 2/3. So our answer is x3 over 3 minus 2x squared plus x plus 2/3. Question 5b asks us to take the derivative of the integral from 1 to x of t squared minus 4t plus 1 dt. In 5a, we just calculated that definite integral, so when we take the derivative of that definite integral, we get the derivative of x cubed over 3 minus 2x squared plus x plus 2/3, and that gives us x squared minus 4x plus 1. Now suppose we were asked to take the derivative with respect to x of the integral from 1 to x of the square root of t squared plus t plus 1 dt. How would we do this? We cannot take the integral of the square root of t squared plus t plus 1 by use substitution. We know of no way to actually take that integral. And yet, we are not actually being asked to find the integral. We're asked to find the derivative with respect to x of the integral from 1 to x of that expression. The second fundamental theorem of calculus states that the derivative with respect to x of the integral from a to x of f of t dt is simply equal to f of x. And the derivative with respect to x of the integral from a to u of f of t dt is equal to f of u times du dx. This says that since the derivative and integration processes are inverses, then the derivative of the accumulation function is the function itself in terms of the variable in the limits of integration. So even though we cannot integrate the square root of t squared plus t plus 1 dt, to take the derivative of the integral from 1 to x of the square root of a t squared plus t plus 1 dt, the second fundamental theorem of calculus says that our answer is simply the square root of x squared plus x plus 1. 6a through d ask you to take the derivative of a definite integral. They look very complicated, but in reality can be done in one step using the second fundamental theorem of calculus. 6a asks us to take the derivative with respect to x of the integral from 1 to x of the square root of t squared minus 1 dt. We cannot integrate the expression, but we do not have to. all we do is replace the t with an x, and our answer is the square root of x squared minus 1. 6b asks us to take the derivative with respect to x of the integral from 2 to x of sine squared of 2t dt. Again, we cannot take that integral. We cannot integrate sine squared of some function. However, we can use the second fundamental theorem of calculus and easily state that our answer is sine squared of 2x. Note that the lower limit of integration makes no difference to this problem. 6c asks us to take the derivative with respect to x of the integral from x to 3 of t cosine t dt. We could integrate this expression using integration by parts, but it's much easier to use the second fundamental theorem of calculus. We will reverse the order of limits, making it from 3 to x, and make the expression negative. So this becomes negative derivative with respect to x of the integral from 3 to x of t cosine t dt, and therefore our answer is simply negative x cosine x. In 6d, we're asked to find the derivative with respect to x of the integral from pi over 2 to x squared of e to the square root of t dt. Using the second fundamental theorem of calculus, we will replace the t with an x squared. So we get e to the square root of x squared, but we must then multiply it by the derivative of x squared, which is 2x. That, of course, is the chain rule. So our final answer is 2x e to the x.